Hello, calculus fans! We're going to talk about curvature now. Let's say we have a smooth curve that's defined by a vector function r. Remember that in a smooth curve, the derivative is never equal to the zero vector. Now, we defined the unit tangent vector before. It's simply r prime over the length of r prime. And since C is smooth, we know that r prime is not the zero vector, so we're not doing anything foolish like dividing by 0. Also, the unit tangent vector indicates the direction of the curve. Here's a picture that shows how this unit tangent behaves. So the curve C is in blue. The unit tangent vectors are all in red. One thing to notice on this picture is that these unit tangent vectors are all the same length. They are, after all, unit tangent vectors. And they're tangent to the curve. They're showing the direction that the curve is moving. And we can see that this unit tangent vector changes direction very slowly when the curve is reasonably straight, but it will change direction more quickly when C turns more sharply. So the curvature of a curve is a measure of how quickly the curve changes direction at that point. To be specific, we're going to define it to be the magnitude of the rate of change of the unit tangent vector with respect to arc length. We're going to parameterize by arc length so that the curvature does not depend on the parameterization. You see, curvature needs to be an intrinsic property of the curve. It's a physical property of the curve, and it should not have anything to do with how you are parameterizing the curve. Let's make a definition to say that the curvature of a curve is the magnitude of dt by ds. T is the unit tangent vector, and here we're differentiating with respect to arc length. We're going to use the Greek letter kappa for curvature. That's not a K, that's a kappa. That's just a traditional thing that mathematicians use to represent curvature. It looks like a sort of a very short capital K in a way. Now, what we'd really like to do is be able to compute curvature using any parameterization rather than depend on having a curve being parameterized by arc length. After all, it's not always possible to take a curve and reparameterize it by arc length. Sometimes the computations can be very messy. Let's use the chain rule to rewrite. We'll be able to say that the derivative of the unit tangent with respect to t is equal to dt by ds times ds by dt. That's just the chain rule in action. And that means we can rewrite our expression for kappa to be the magnitude of the derivative of the unit tangent with respect to t divided by the derivative of s with respect to t. And remember that ds by dt is just the length of r prime of t, so here's our final formula for the curvature. The curvature can be computed by taking the length of the derivative of the unit tangent divided by the length of the original vector. We'll use this now to compute various values of curvature. Okay, that's all for now.